Hello everyone, thank you for coming to this talk about hybrid AI-assisted visual analysis framework to study the effects of cloud properties on climate patterns. This is a joint collaboration between multiple institutes, primarily led by Palo Alto Research Center and University of Victoria. Clouds play an important role in modulating Earth's climate by controlling the overall radiation budget and thus shaping the coupled circulation of atmosphere and ocean. In turn, this drives regional changes in climate variables like temperature and precipitation. This makes cloud ideal for climate intervention techniques like marine cloud brightening, which refers to modification in cloud reflectivity by changing the low clouds using sea spray aerosol injection, thereby cooling the surrounding regions. However, to avoid the unintended effects of MCB or marine cloud brightening, we need a better understanding of how cloud properties impact large-scale global circulation and regional climate patterns. Because of climate teleconnections, an MCB experiment on a particular region can have unintended effects in different parts of the globe. And designing such an intervention technique with conventional Earth system models or ESM models is computationally expensive because it requires testing out different design and hypothesis intervention scenarios. And it takes a lot of time to run these expensive simulation models. So our idea is to propose a hybrid AI-assisted MCB intervention scenario analysis framework. Here is the overall idea of our proposed pipeline. So we train hybrid AI models using physics constraints and geospatial domain-aware preprocessing of the data. And in the front end, we have an interactive visual analysis system for our scientists to use and perform different MCB intervention scenarios in a rapid exploration fashion. Our suite of hybrid AI models are essentially physics-informed machine learning models that emulate the response of global circulation to change in climate patterns. In other words, we want to replicate or create a cloud-to-climate response function. Our entire problem formulation is based upon the fundamental statistical principle of fluctuation dissipation theorem or FDT, which states that the response of a dynamical system to a perturbation can be inferred from the time-lagged correlation statistics of natural internal fluctuations in the system. We perform a bunch of preprocessing activities to extract these natural fluctuations from the climate fields that we extract from the simulation runs. At a high level, the three main stages or three main characteristics of our proposed hybrid AI models are: we transform the 2D regular grid sample data to a spherical sample data to inherently capture the spherical orientation of the data across the poles and different geospatial regions. We train a suite of hybrid machine learning models or physics-informed machine learning models which predicts the input fields, which are essentially the cloud radiative properties, and the outputs, which are essentially the climate variables like temperature, precipitation, and surface pressure. We train these models for different lagged durations. For example, we train it for 1 lag duration, 1 month lagged duration for 2 months, and consequently up till 36 months. So using the principles of FTT to predict the long-term climate projections from this kind of models, we essentially do an integration of these different machine learning models to come up with the eventual effect of climate for the change in cloud radiative properties. We also have trained our models using physics constraint to preserve the generalizability and also the physics properties in our model. So we use 4 physics constraints or soft laws, which is non-negative precipitation, atmospheric moisture budget, atmospheric mass budget, and atmospheric energy budget. Please refer to our paper for full details and evaluations of this system. Using this back-end suite of hybrid AI models, we have designed a front-end interactive visual analysis system which lets our scientists explore different MCB experiment scenarios and understand basically the properties of how changes in cloud properties or radiative properties of cloud is related in long term for different climate variables across different parts of the world. Details about this visual analysis system is available in our paper, but to highlight the key features that we have implemented here which helps our scientists, we'll go over some of these features in this talk. So based on the requirements set forth by our scientists, we have implemented four different features to help address those requirements. The first is a free-form selection to perform different MCB perturbation experiments. So essentially the users can go ahead and select the regions that they want to perform marine cloud brightening for, and also a panel on the side which also lets them set different variables and parameters that are associated with such an MCB experiment. The next feature is out-of-distribution tracking. Since we are using an AI or a machine learning model to make these predictions, we all know that machine learning models are susceptible to distribution shift. And in our case, we are providing inputs by perturbing the field, which can easily lead to a situation where we provide an input which the models have never seen before. It's totally out of distribution. So we want to track that, and using a panel in our visual analysis system, we show how far off the newly created points, as shown by the red dots here, are versus to the known distribution that the model has been trained for, as shown by the contour plots in blue. So this lets us or associates a sense of trust to the predicted results. If a particular perturbed field is very far off from the known distributions, probably that's not a robust or a reliable result to use for experiments. The next important part of our visual analysis system is to track the risk of performing marine cloud brightening on different climate tipping point regions. So we have identified 7 different climate sensitive geospatial sites across the globe. Each have their own conditions that can lead to climate tipping points, which refers to a point where the climate or the situation or the environment around that region can never be reversed back. So we want to avoid those kind of scenarios when performing an MCB experiment. We simulate that scenario in our visual analysis system and try to highlight that with a color red, indicating that because of performing a particular MCB experiment, these sites can lead or can be triggered towards a climate tipping point. So we have covered 7 regions across the globe, and each of them have different criteria for tipping points. You can read about the details in our supplementary material as well as in the manuscript. Another important feature of our visual analysis system is to progressively store this interesting MCB experiment settings so that it can be later downloaded and can be used to run the expensive CSM or CSM models. We have performed different sets of evaluation studies to compare the prediction results performed by our hybrid AI models. Mainly, we have compared the forcing responses against CSM2 runs on 3 specific geospatial sites that the scientists have particularly studied before. These are the Northeast Pacific region, Southeast Pacific region, and the Southeast Atlantic regions. Here is a small screenshot from one of these studies that is performed on the Southeast Pacific, where we are perturbing a particular section near the Southeast Pacific for 10-year duration, and we are changing the shortwave surface radiative effect on as well as the shortwave top of the atmosphere radiative effects. Because of performing this experiment for a 10-year duration, we try to understand what is the impact on the average temperature for these 10 years after performing MCB. The right hand side shows the increase or decrease in temperature across different spatial sites. As you can see on the region in Southeast Pacific, the average temperature for 10 years significantly reduces where we have performed MCB experiments. But one thing to be concerned is that different sites across the globe have seen an increase in temperature, which can lead to different climate tipping points. So our tool essentially helps us or helps the scientists understand what can be the possible consequences and where and how MCB experiments needs to be performed before going ahead and experimentally deploying them. We would like to thank our funding agency DARPA, and this was funded under the DARPA's AI initiative for climate tipping point modeling. And you can visit our documentation on the website for this project to learn more about the data sets, the methods, and different aspects of our project. Thank you for listening.